Section 4.2 is called Prime and Composite Numbers. It's going to continue our discussion about divisibility, how things are divisible by one another. We're going to start with a little bit of vocab so that we have a sense of how we're working through this together. And the first vocab word we're going to look at is the word prime. A prime number is any positive integer, we could also say whole number, any whole number, with exactly two, I shouldn't even say whole number because it's positive integer, so not just whole number, but natural number. That's the word I want. With exactly two distinct positive divisors. What does distinct mean? Different, and that's important. So when I list my prime numbers, what is the smallest prime number? Zero is not a positive integer. 1 doesn't work. Why?
Because we just 1 and 1.
Yeah. 1 does not have two distinct divisors. But I'm glad you said it, because that's my whole point, is that we often think about the number 1 and we sort of in our mind think, oh, it's prime, and it isn't. It is not a prime number. It's not a composite number either in a moment. It's neither. And it's sort of by himself in that category. So what's the smallest prime number? 2. All right, so let's do a few of these. We're going to give the first few of them. I'm not going to go forever because that's not possible, but let's give the first 6 of them. 2. What's the next prime number after 2? 3 is correct. What's after 3? 5 works. And then 7 is right. And then 11. Why did we skip 9? Because it's divisible by 3. Why am I skipping all the evens? Because they're divisible by 2. Okay, we're all on the same page. Good, just checking. Let's do one more of them, because I said we were going to do 6 of them. The next one is 13. Very good. All right, so this process continues. We skip anything that's actually divisible by something else that we already started with. Okay. Composite. Composite numbers are any positive integers, or natural numbers is another word for that, with more than, that's the phrase that's important there, more than 2 distinct integers. So listing these is a little bit more complicated because there's more of them actually. So I don't necessarily want to go in order. I just want you to give me an example. What's an example of a composite number? 4 is and it is actually the first one as well. What's another one?
6.
Okay. Let's jump around. Give me a 2-digit number that's composite. 24. All right. Give me one more 2-digit number and then we'll stop this silliness. 21. Okay. So there's lots of composite numbers. What does it take for it to be composite? Well, it takes the ability to be broken down into some other factor besides itself, or 1. That's all it takes for it to be composite. So the majority of numbers are composite numbers, right? Yeah, they are. Factorization is simply any expression of a number in factored form. So, for example, if I have the number 12, tell me one way I can break the number 12 down into 2 factors. 3 times 4. All right, there's another way I could break that one down, right? Into 2 factors. I could do 6 times 2. Okay, so factorization typically is not a unique thing. There's often more than one way, not always, but there's often more than one way to break a number down into factors. Okay? Prime factorization is a little different. Prime factorization is a way of breaking down the number into only prime factors. So what would I have to do with the number 12 to make that happen? Right. I'd actually need to take, in this case, the 4. That's the problem I did before. And I'd have to take the 4 and break it down as well. So I may have more than 2 factors then when I'm done, right? I might not. I could do the number 15 and it's 5 times 3 and we're good to go. That's cool. But I might have more than 2 factors in order to be able to make it a prime factorization. Now there's something about prime factorization that's really important though. Prime factorization is unique. Let me actually skip over to that real quick. Just go ahead and flip your page to the next page where I did that because I think this fits a little bit better here. Prime factorization is unique. This is the fundamental theorem of arithmetic. It says the following. Each composite number can be written as a product of primes. Okay, that's cool. I can break it down into primes. But the important part is that it's in one and only one way, except for the ordering. For example, 15. 15 is 5 times 3 and 3 times 5. We wouldn't call that different. Okay, just moving the numbers around is not considered different. It would, however, be different if I had another way of writing out different numbers besides just 3 and 5 that make up 15. So prime factorization is unique. There's only one way to take a number and to break it down into its prime factors. All right, the reason I actually thought it fit here really well is because that's exactly what we're going to do in the last example, the one that I skipped that we're going to go back and do now, is we're going to break it down. And when we break this down into its prime factors, we will all get the same answers. There is one and only one answer for this type of a problem. So let's go back to do that example now. All right, it says find the prime factorization for each of the following. The first number we have is 23,660. There's two ways that we could do this that I'm aware of. There probably are others, but there are two very, very clean ways. I know that you've seen at least one of them before. You might have seen them both. So let me ask you, what way have you seen to break this down into prime factors before? Factor tree, and that's usually the one people have seen. So let's do a factor tree, and I want you to tell me what two factors do you know will go into and compose together to make 23,660. 2 would work. Can we do something bigger so my factor tree doesn't go on forever? What's it end in? It ends in a 0, so this is going to be divisible by 10, right? Let me do 10 and what? 2366. Okay, the 0 at the end at least lets me break it down into 10 times that. Now, in a factor tree, I'm only done with the branches in the tree when I get to prime values, and 10 and 2366, neither one are prime. So I have to continue this factor tree under both of those numbers and break them down. So the 10 becomes what? 2 and 5. And as you finish the end of a branch, it's really helpful if you'll circle those numbers so you don't lose them in the process. Because factor trees sometimes can get really long or really spread out, and it's really easy to overlook one of the numbers. Okay? All right, 2366. Now this might be one where you're looking at it and you go, okay, I don't know what this one's divisible by, but I know it's even. Okay? Makes sense. And so if that's the case, go ahead and you can use the 2. There was nothing wrong with using 2 at the beginning either. I don't want to dissuade you from doing that. It's just that we could do it a little bit quicker if we used a bigger number. What do I get when I take 2366 and I divide it by 2? 1183. Is that okay with you guys? All right. I am done with this 2 because 2 is prime. 1183, it isn't prime. So let's actually think through what we know it's not divisible by. I know it's not divisible by 2. Why? It's not even. How about 3? Can you check 3 for me real quick? Why is it not divisible by 3? The sum's 13. 13 doesn't divide by 3, so 1183 won't either. 5. Doesn't end in 5 and a 0. Okay, what's the next prime number after 5? 7. We don't have a rule for 7, so grab your calculator really quick and tell me, does this divide by 7? It does. And calculators are very appropriate for what we're doing in this particular section. When kids are starting to do factorization, they're usually using calculators to do it. Maybe not always, but for your sake right now, we're going to use them. It's not a problem for me. 7 and what? 169. Now, is 7 prime? Yeah, so I'm done with that branch. 169, however, is not prime, and it's probably a value that you have seen before. What is 169 broken down? It's 13 and 13. Most kids, I don't want to say most kids, but it's common, let me say it that way, it's common for kids to memorize the squared numbers up to about 15. So they know, like 8 squared and 10 squared and 12 squared and 15 squared. So 13 squared would be one that would be reasonable for us to have memorized at some point. You may not have, but it would be a reasonable assumption. All right. Now, we want to make sure we actually answer the question that's asked, which is, what's the prime factorization? Right now, I did all the work for it, but haven't answered the question. So how do we answer the question? Well, what we do is we take, and you usually see it written smallest to largest, but that doesn't have to be the case. Usually, though, we would start with the smallest factor, which is 2. And how many of them are there? There are 2 of them, so we would write this as 2 squared. times. What's the next smallest factor? 5 times a 5, and there's only one of those, right? You can put an exponent of 1 if you want to, but there's certainly no need to. After 5, the next smallest digit is 7. That's a factor, right? 7, and it's only got one of those. And then I have 13, and there are 2 of those, so it's 13 squared. This is the prime factorization for the original number as given. How can I make sure I'm right? I multiply all those together, right? So there's no reason at the end of this particular problem not to be very sure of the fact that you got the answer right, yeah? You don't need a back of the book. That's a handy thing. All right, so these factor trees are very common. Who has done factor trees before? Let me just raise your hands. Okay, just about everybody. Cassidy, you haven't done?
Like the upside down.
That's the one I'm doing next. Cassidy, awesome. Okay, Cassidy's seen the other one. The other one's my favorite too, and I'll tell you why after we get it done. 23, 6, 60. Do you remember how you started that one, Cassidy? What did you do?
The upside
Mm-hmm.
down. And then started with like a biggest.
I always started it with the smallest one, the smallest number that you could divide by. But you could start with the biggest. I think the reason we never did start with the biggest is because it's easier to see the smallest. So I'm going to go with the smallest because of that. I mean, like looking at this number, I don't know that it divides by 13, except that I already did a factor tree to know it. But I do know looking at it automatically divides by 2. Okay, so we're going to start with the smallest number that you know it divides by. We do need to only be dividing by primes in this case. Okay, it's not going to work if I divide by something that's not a prime. So I'm going to do the smallest prime number. So what is 23,660 divided by 2? 11,830. 11,830 is still divisible by 2 because it's still even, right? So we'll divide it by 2 one more time. What is this divisible? What does this give you when you divide by 2? What was it? 5915. And then it's no longer divisible by 2, right? Okay. The next prime number would be 3. So let's add those up. Does this divide by 3? It does not. Okay. So then we go to 5, which is what some of you were already telling me to do. So divide this by 5. What do you get? 1183. Wonderful. Now, we do not need to keep testing 2 and 3 and 5. We've already tested them. It's not going to keep working. So we keep going up our factors of primes, our prime factor list. So we don't need to do 5. The next one would be a 7, and we would attempt to do that one. So when I divide this by 7, I'll get that same 169 that I got before. And then technically what we would do next is say, okay, does this divide by 7 again? And you could try it, and it doesn't work. So then you say, okay, what's the next prime number? 11. You might divide by 11, and you find it doesn't work. And then you would end up with 13. There's no reason to do those if you recognize already that it does divide by 13. That's cool. You can use that. But if you weren't sure of the value, right, like if it weren't 169 and it were 171 and you didn't know, or 173 or something like that, then you could just go up the list of primes. All right, so the answer, of course, is the same. I have 2 squared times 5 times 7 times 13 squared. Pros and cons. There's absolutely nothing wrong, technically, with either of these. Tell me some pros and cons you see just looking at how these are written out, at their displays, at how we did the process. What's a benefit to one of them? Pick one and tell me what you like about it.
On the factor tree, you can see the 2 things are divisible.
That's true. So when you do the factor tree, you sort of see the breakdown in the 2 values right there on the tree. That's a good pro. All right, what else? The upside down has the feature that the answers go from smallest to biggest, and they're just right here all together. It's a pretty nice feature. And if I have gone in order, then I've got all the 2s together, for instance, and all the 7s together and whatever I have. Yep. Any other pros to either of them that you see? One of the pros that I like about the factor tree is that I can do it in any order, and it doesn't have to be divisible by primes. I don't have to just look at primes when I do that one, right? I divided by 10, and that was kind of friendly, and it made it break down sort of quicker. I don't have the ability really to do that with the other diagram very well. There is a con that goes along with a pro that Jessica mentioned. Jessica mentioned on the upside down division one right there that they're sort of all in order from smallest to biggest. A con to the factor tree is it's really easy to lose one of your factors in the work. I circled them all in orange so we wouldn't lose my factors. But it's very common to lose a factor in the middle. The factor that students would probably use on this, on this factor tree is that 2. That's probably their most likely factor to get lost in the mix. But it's really easy to lose a factor if you're not being extremely careful as you're doing it. So do you have to lose a factor? Well, of course not. Can you be really careful? Of course you can. But it's just something to be aware of as you're working through them. Okay? Now, the next problem is not going to be so helpful to do with either of these methods. It's a different kind of problem. 16 to the 4th, 81 to the 4th, 6 to the 6th. This particular problem is already partially factored, right? I've got numbers raised to powers. I mean, that's a good thing. But what do you notice about each one of those bases? 16, 81, and 6. What's that?
Oh, just kidding.
Okay. They're what? They're composite numbers. None of those numbers are actually prime. And even if some of them have been prime, not all of them are prime. Okay? So let's start with the 16. And you can do it with a factor tree if you need to, or you might just know it looking at it because you've worked with some number like 16 before. But what is 16 broken down? Okay, 2 times what? 8. 2 is prime, 8's not, so 8 breaks down again. What's 8? 2 times 4. 2 is prime, 4 is not, so what is 4? 2 times 2. So 16 is a lot of 2's. How many specifically? 4. So over here, this 16 I'm going to rewrite as 2 to the 4th, but this 2 to the 4th still has a 4 on the outside of it. Is everybody okay with that? Now, let me tell you something that would be unhelpful to do in this particular problem. It would be extraordinarily unhelpful to multiply this all out. Right? If you actually took your calculator and said, what is 16 to the 4th times 81 to the 4th times 6 to the 6th, the number is going to become, number 1, huge, and number 2, you're going to have to undo everything you just did with a factor tree later anyway. Okay, so taking something that's already in factored form and then multiplying it out would be counterproductive. So that's why we're continuing to just break it down. 81, let me do 81 with one of those with the upside down division just for practice. 81, what is the smallest prime number that divides 81? 3. How did you know 3 worked? I mean, 81's not in my 3's tables. Because 8 plus 1 is 9. Okay, good. All right, so 81, what is 81 divided by 3? It is 27, right? And if you don't know it, then you just grab a calculator and it'll tell you, right? What is 27 going to be divided by, the smallest prime number? Another 3. Now you're in your multiplication tables. 27 divided by 3 is 9. And then 9 divides by 3 again, and it gives me 3. So this is actually 3 to the power of 4. It's almost exactly what we did in the last problem, just with the other method. So 81 is also 3 to the 4th. Okay, something to the 4th, in other words. And it's got another power 4 on it. Okay, I don't think that 6 is complicated enough to really deserve to be drawn out. What is 6? 3 times 2. And just for the sake of doing it right now, I'm going to write it as 3 times 2 with a 6 on the outside, kind of like I did the other ones. Now, we had a chapter or section in our last chapter that talked about what to do with problems like this. This is an exponent problem, right? So what do I do when I have an exponent to an exponent? I multiply. This is 2 to the 16th. Okay, when was it that we add? When you have another base, which we will have in a minute. We'll do that in a second here, yeah. But we don't have another base here. We just have 2 raised to the 4th to the 4th. Okay, so that's multiplying. How about the 3 to the 4th to the 4th? 3 to the 16th. Okay, the last piece is different. This is 3 times 2 to the 6th. What do we have to do with that? Yeah, it feels like a distribution, right? So what will it end up looking like? Good, 3 to the 6th times 2 to the 6th. All right, so now taking a look at this, what do you see? 2, 3, 3, 2. What do you see? Like bases. Now they've got some bases that actually match. So let's just go in order from left to right. This is 2 to the 16th. Is there another 2? Sure there is. I have 2 to the 16th and 2 to the 6th. So now what am I going to do with those exponents? That's when I add. So this is 2 to what power? 22nd. And then I have the 2 in the middle, which are both 3s, 3 to the also 22nd. Is everybody good with that? Okay, the next one's different yet again. I wanted to make sure you saw 3 different kinds of problems because I think that I know you've done stuff like this before, but maybe not all compiled together. The next one is unique. It looks quite different than the last one. What about this makes it so different? There's a plus. There's addition in the middle of this problem. So that makes it do something different. Now, looking at these, though, let's compare the values in each part of it that are separated with addition. What do you notice that's the same and what do you notice that's different? Let's start with the same. What do you notice that's the same? They have the same bases. That's an important thing to notice. Okay? What do you notice that's different? Some of the exponents are different. Not all of them, though, right? Okay. Some match, some don't. So let's start with the base 2. They don't have the same exponent, right? The first one is squared, and the second one is the power of 4. So squared means I actually have 2 2's. To the power of 4 means I have 4 2's. So how many do they have in common? They have 2 2's in common, right? 2 2's in common. 2 2's in the first one, 4 2's in the second one. So they have 2 2's in common. Not 2 2 like the skirt. 2 2's. You with me? All right, fabulous. Okay, so what we're going to do is we're going to factor out the 2 2's that they have in common. Now notice when I factor the 2 2's out of this one, there aren't any 2's left. But when I factor the 2 2's out of this one, how many 2's are left? 2 of them. And you could write that as 2 times 2. You could write that as 2 squared. Doesn't matter what you want to do. Actually, I'm sorry. I want to write this over here. Leave a space. 2 2's. Oh, and I'm going to put that plus sign in between. Right now, I don't know if I need anything in front or not. Okay? So I'm just sort of mirroring the process where I have a number plus a number. Here's my number plus a number. Okay? Let's move on to the 3's. How many 3's are there in the first term? 5. How many 3's are there in the second term? There are 4. How many 3's then do they have in common? 4. So I'm going to take and I'm going to pull out all 4 3's that they have in common. So if I take the 3 to the 5th right here, and I pull out 4 of those 3's, how many are left? 1. So there is still a 3 that is left in this first piece. If I take the 4 3's here and I pull out 4 3's, how many are left? None. There aren't any left. I don't want to write down 0, but I have 3 raised to the 0. That is, there are 0 3's left, so I don't need to write anything down. Okay? Everybody good so far? I pulled them all out. Remember, factoring is the same as division. What's that?
Oh, why are you writing it in that, like, order though?
I'll show you when we get to the end. I think it'll all piece together and make sense, but if it doesn't, you ask me again. Okay? Definitely ask me again. What do you see about the 7's? They're the same. They both have 7 to the 55. So I'm going to pull out the 7 to the 55, and that's completely and totally pulled out in front now. There are no more 7's left, correct? Okay, everybody good so far? Okay. 2 squared, 3 to the 4th, 7 to the 55th. That's all primes raised to powers. What is left on the inside? What is this stuff? What is 3 plus 2 times 2? That's 7. So I was able to combine the pieces that they don't have in common with the addition that they were using to combine them. And then what did we find? Well, we found another 7. So how can I rewrite this one last time to actually combine all the pieces together now? I've got 2 squared, and then what do I have? A 3 to the 4th, and then what do I have? I have 56 7's now instead of 55. So I'm trying to make it easier on myself by pulling things out that they have in common so that what happens that's in that circle there, right here, at the end is the least amount of stuff that's left to actually really combine. So by combining the least amount of stuff left at the end, I reduce the amount of work I have to do. Are you okay now, Madison, with the processing that I did to get there? Okay. Does anyone else have any other questions about this one before we move on? Okay. We're going to go through a few more theorems. We're not going to get through much more today, but a couple more theorems. So this is Theorem 412. We already talked about this one. There's one and only one way to do this. Okay. And then Theorem 414 is an interesting one. It says that if D, is a divisor of n, then n divided by D is a divisor of n, which sounds really weird, but it actually is something you know to be true. And let's just do an example real quick. And we're going to do an example of the number 32. I want you to tell me one number that divides 32. I don't even care what it is. Any number you want. Prime, not prime, whatever. 4. Okay. So 4 divides 32. That's this first part. We've got a number that divides 32. According to this, then the number 32 divided by 4, which is what? 8. That gives me 8. Then 8 would also divide 32. Does 8 divide 32? Yes, it does. The net result of this theorem, what this theorem is actually saying, is that your divisors occur in pairs. Well, you know that. That's what your factor tree does, right? It's what the division part does as well. Every time I divide it, I get another factor of the number. It may not be a prime one, but I get another one. So no matter what number you give me, so let's say we did the number 64, I'm able to create a factor tree with 2 specific branches, and both of those numbers will multiply to give me 64, and both of those numbers will each individually divide the 64 that I started with. So all this theorem says is these occur in pairs. All right, we'll do the last 2 theorems. These 2 theorems go hand in hand, so I want to always present them together. Theorem 415 and Theorem 416. 415 says if you have a composite number, okay, if it is a composite, then there will be a prime factor, and if you take that prime factor and multiply it by itself, it will be less than or equal to your composite number. And you should look at that and say, okay, that's kind of a cool trick, so what? And that does not really look like it's a helpful piece of information. 416 is a bit more helpful because it actually tells you something on how to use 415. It says if you have a whole number bigger than 1, okay, great, and it's not divisible by a prime number where the prime number squared is less than or equal to n, then n is prime. So let me tell you what this actually really boils down to. Let's say you had a number and you didn't know if it was a prime number or not. Maybe you had the number 431. And you're going, okay, well, I can test the numbers, right? I can divide it by 2. It's not going to work. I can try to divide it by 3. It's not going to work. I know it's not divisible by 5. And you start, trying to divide by things, right? The question at some point becomes, when do I get to stop trying to divide it and decide it's prime? It's a legit question, right? I mean, when do I actually get to stop and actually say, yep, it's prime? And what happens if I stop too soon and, oh my goodness, I thought it was prime, but all of a sudden I find out it didn't divide by anything until I got to 43. How was I supposed to know I needed to go all the way to 43? This is a legit question, don't you think? Like, how do I know when to stop? These theorems actually tell you when you get to stop. You get to stop This is so not mathematically good that I'm going to write this down this way, but we're going to do it anyway. You get to stop trying when you get to square root of your number. And you might be looking at that and say, where'd the square root come from? Well, it came from right here taking a square root of both sides. Okay, so let me give you an example, not the example that's in your notes. We'll just give you another example, and then we'll do the one in your notes next time. Let's say you had, what did I say just a second ago, 143? Is that what I gave you? I think that's what I said. 143. Take a look for me. I want you to take the square root in your calculator. What is the square root of 143? I'm hoping that it's not something that actually is a whole number. Is it a whole number? 11.95. So what is this theorem saying? Well, this theorem is saying that I only need to divide it by the prime number smaller than that. That's not very many, is it? 2, 3, 5, 7, and 11. And once I get to 11 and I find out none of them worked, I know it's prime. There's no need to do a 13. There's no need to try 17. I don't need to go to 19, and I certainly don't need to keep going after that. I get to stop at 11. That's really handy. Okay? So we're going to come back to that idea next time. We'll put a stop on this today.